Alright, Mrs. Howard's chemistry class, this is PowerPoint number 7, the last one on Unit 12, acids, bases, and salts. And we're going to focus on defining pH and using the hydrogen or hydroxide ion concentration to calculate the pH of the solution. And we'll do much of this calculation in class. Alright, so Roman numeral number 6, pH is the power of hydrogen. And the pH actually means, the P in the pH actually means the negative log. And specifically, it's talking about you take the negative log of the hydrogen ion concentration. So, capital letter A, water naturally ionizes, we talked about this last time, into the hydronium ion, that's the H3O+, or sometimes remember they refer to it as the H+ ion, and the hydroxide ion. So you think about water, HOH, and you take off the H, and you have the OH over here, so you have those ions. And it makes it a very weak electrolyte, so much so weak that you can't even really call it a weak electrolyte. You just say it doesn't really conduct electricity in water. So when you see the balanced equation down on the bottom, you have H2O, and then we're showing it as the hydronium ion, so that's why it's got the H3O plus the OH negative ion. So one of those hydrogen H+ ions hooks up with another water molecule, and so you get the H3O+ ion. That's what the ionization of water. It formed ions where there weren't any to start off. You know, like the chemical equation, you have, for an ionic compound, you have a metal plus a non-metal. You chemically put them together and you get an ionic compound. Water's not like that. Hydrogen's a non-metal, oxygen's a non-metal. So when you get this, when you say something ionizes, it's creating ions where there just weren't any there before. Alright, capital letter B. Pure water, again, will self-ionize to produce a molar concentration, that's moles over liters, of, here it is, 1 times 10 to the negative 7 for the hydronium ion, that's the H2O plus, or the H+ ion. And, strangely enough, 1 times 10 to the negative 7 moles per liter for the hydroxide ion. And that's, you know, blah, 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 25 degrees Celsius, 298 K. We don't really care about that right now, right? So these are the concentrations. So however many H ions you have just an equal amount of hydroxide ions. Using that information, this is how we can come up with the pH scale. So we have some numbers and we have some constants that you're going to have to know. So they have a K, a constant for water, and the constant, it's called Kw for water, is always 1 times 10 to the negative 14. And notice that the pH scale goes from 0 to 14. 0 to 14. So 1 times 10 to the negative 14 is Kw. And when you look, it says right beside that, and Kw is equal to the hydronium ion concentration, that's the H3O+, and times the hydroxide ion concentration. So you see the little square brackets again, that means concentration. So we know that the number Kw is always 1 times 10 to the negative 14, it doesn't change. And if we know either the hydrogen ion concentration or the hydroxide ion concentration, then we can figure out what the other one is. So they have to give you 2 of those numbers, and as long as you can have 2 of them, then you can come up mathematically with the other one. When one goes up, the other goes down to reach equilibrium. And Le Chatelier was the guy who said, hey, if you have this whole system and it's kind of balanced out in equilibrium, if you mess with one side, yeah, it's going to kind of get wonky for a bit, but then it's going to come to a new balance or a new equilibrium. If you know Kw, that's letter B right there, if you know Kw, which you do, it's 1 times 10 to the negative 14, and you know one of those 2 concentrations, then you can calculate the other. Letter C, since the pHs are so freaking small, they found another way to express them. Remember, instead of writing 1 times 10 to the negative 14 or 1 times 10 to the negative 1 times 10 to the negative 12, then what they did is they said, hey, let's just make it easy, and it doesn't look easy. POH, or pH, is the negative log of the hydrogen ion concentration. So that's where they come up with the pH is 7.2 or 7.4. Instead of saying it's 1 times 10 to the negative 7.4, then they can give you a pH in a different form. So number 1, pH is the negative log of the hydronium concentration. And number 2, the pH ranges from 0 to 14, which you already know that. It's going to take me just a couple more minutes to finish this. Letter D, POH deals with the hydroxide ion concentration. You know, we don't talk much about the POH. We always talk about the pH, and that's okay, but know that there is also a POH out there because the state of Texas expects you to know that, children. So the POH deals with the hydroxide ion concentration. And so when they say POH, they're talking about the negative log of the hydroxide ion concentration. And when you see that negative log thing and it looks kind of ugly with those brackets around it, don't freak out, because you just punch the buttons on your calculator and everything's happy. So you hit negative, and you hit the log button, and you hit whatever concentration that is for that. Now, if you look at capital letter E, the pH plus the pOH is going to equal 14. Remember, the pH system goes from 0 to 14. Water's at 7 because it's got just as many hydroxide ions as it has hydronium ions or hydrogen ions. All right, titration. Titration is a process of adding a certain measured amount of solution that you know everything about. You know the concentration and everything, and you're going to use that known to figure out the concentration of a solution that you don't know. Right? That's the process of titration. It's kind of tedious. You have to be really careful with it, and you have to be, sometimes you even have to come down to where you're counting drops of how many pieces you put into it. So let's say that I found this bottle of acid in the cabinet, and somebody made it and they forgot to write on there what the concentration was. Well, I would use the titration process to figure out what it was. I would take the known, like a base, because I know bases and acids react with each other. I would take a base that I knew everything about. I knew the concentration and everything. And then I would take an indicator and put it in my acid, and then I would start adding the base in a certain amount. And when I got to the point where it changed color on me, then I know I've equalized them. I've got to that equilibrium point. So I know that I have the same amount of moles of base that I have moles of acid. So you use this equation called M1V1 equals M2V2. It's an easy equation to use. The capital M is molarity 1. So you have my acid, say that I didn't know what the concentration was, so I'd have a question mark there. That's my X. I'd have the volume of that one, so let's say I used 25 milliliters. And then it says equals M2, so here's my base. I know the molarity of that. I'll write it down as a number. And I have to figure, well, how much of the volume, how much of the base did I put in with that acid? And then I'd have 3 numbers, and I could calculate or solve for the fourth number. That's just basic algebra. We'll do some of these in class, just a few of them, so that you understand what's going on. If you're in pre-AP, we'll do a lot more than a few. Roman numeral number 7, then titration. Capital A, you've got some equations to use. The first one is M1V1 equals M2V2. Those are on your 8 pages. Number 2, start with the balanced equation for the neutralization reaction. You always have to start with a balanced equation. If you don't have the balanced equation, stop and get it. Number 3, you've got to determine the number of moles of the acid or the base, whichever one you're working for, from the known solution used during the titration. So you have to know, here's the molarity. How do I get moles out of that? And molarity, that capital M, is just moles over liters. Number 4, determine the moles of solution of the unknown solution used during the titration. And number 5, determine the molarity of the unknown solution. It sounds really complex, and like molarity this, and molarity that, and concentration there, blah, 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 and you get kind of lost in all the terms. It's really not so bad once you do it, and we'll do this in class as a lab. So in a titration, you've got 27.4 mils of a 0.015 molar barium hydroxide. It's added to 20 ml sample of HCl solution of unknown concentration. What's the molarity of the acid solution? So we need 4 numbers. M1V1 equals M2V2. So I'm going to call my M1V1 my first. I'm going to just name the acid, the bases as 1s. So there's a volume of 27.4 mils. There's my V1. And I've got a molarity of 0.0154 molar barium hydroxide. So I've got M1 and V1 right there. Is means equal, so there's the equal sign. And it's added to a 20 ml sample. There's my V2. And my question is saying, what's the molarity? M2, I don't know what that is. So that's my X, my unknown. And we can plug this in. M1V1 equals M2V2. Try this on your paper. Yes, that would be you. Try it on your paper. It's not that difficult. Multiplication and then division. That's all you've got to do. All right, letter G, buffers. Buffers are solutions in which the pH remains relatively constant even when small amounts of acids and bases are added. So let's say your head's not feeling very well. You know, you've got a headache and you want to take something for it. Well, the aspirin that you take is acidic, and you've already got acid in your stomach. You put more acid in it, and you'd think it'd kind of make it too acidic, and sometimes it does. Your stomach gets really upset by that. So what they started doing is they started putting buffers in the medicine, the aspirin that you take, and buffers kind of control or limit how much you can mess up the acidity of something. So when they put a buffer in the aspirin that you took, and then you took it, your stomach doesn't get so upset when you do that. So buffers are going to modify how much the pH changes. It kind of limits or slows down the change in the pH. Now, obviously, if you dump a whole ton of acid into something, it's going to make the pH drop down or go down to become more acidic, but this can kind of control it a little bit. Think about the aspirin that you take or the tablets that you take. They're not a whole lot of the chemical in it, so you don't have to take a whole lot of it. The buffers are usually made from a pair of chemicals. It's made of a weak acid and one of its salts, a salt that you can make from that acid, or it's made of a weak base and one of its salts. It just depends on what you're putting it in and how you want to modify it. So it's made of a pair of chemicals, a weak acid and one of its salts, or a weak base and one of its salts. A buffer system is better able to resist changes in pH than pure water. So we can have pure water and we can add an acid to it and it's going to change the pH. If you do the same thing with a buffer solution, it's not going to change the pH as much. It's going to lessen that pH. Instead of having this really huge drastic change in pH, it's going to lessen that. It's going to resist that change in pH. Oh, again, there's my inertia thing. You can kind of think of it as a pH inertia. It increases the inertia of the pH. Yeah, I know. It's a stretch, but go ahead. Okay, since it's a pair of chemicals, one chemical neutralizes any acid added, and the other chemical would neutralize any additional base that's added. So you have the two chemicals that are working together. It's a pair of chemicals. So you've got one chemical that neutralizes any acid and one chemical that works to neutralize any base. So you have a buffer system that's trying to control the amount the pH changes, either going up or going down. And what's really interesting is that they produce each other in the process. So you have chemical reactions going on, and when the acid part neutralizes any of the base that's in there, you have a chemical reaction that produces the base part. And when the base part neutralizes any acid that's in there, you have a chemical reaction that produces the acid part, or produces the salt part. So you have this whole thing where it's kind of, it's not a perfect system, but it kind of reproduces itself. So again, it tends to control how much that pH is changed or altered. Okay, so again, so what about buffers? Buffers are actually useful things. Buffers, you have buffers in your blood system, in your circulatory system, and you have to have a certain pH in your blood, and you have buffers in that. You have sorts of salts and things in that to control that pH. Medicines, oh my gosh, a lot of medicines, a lot of aspirins. When you think about how much aspirin and Tylenol, all that good stuff you take, a lot of those medicines, they'll tell you, oh, you need to take this on a full stomach, or you need to take it with food. And a lot of times they're concerned about something becoming too acidic and it damaging your stomach, and they put buffers in them to help that. Oh, and we have a lovely cartoon for you children, and I believe we're getting close to the end of the notes. I don't think this is quite it, though.